So 4 theorems about the Euler characteristic and some space invaders. I mean this kind of space invader. Maybe you've seen my group looking at pictures that look like this. This is the old space invader, right? If you want to do topology with this shape, which looks slightly different from what I just did, topology of this shape, say in R2 as a subset of R2 in the plane, is very well understood. You can do all kinds of classical topology with this kind of a shape. But this thing down here, if you consider it as a grid of finitely many pixels, finitely many points in Z2, that is the integer lattice instead of the real plane, that's a different sort of a thing. And that's, nowadays, people refer to that as digital topology. It's the sort of a topological theory which is meant to handle spaces which are made up of finitely many points arranged in some kind of way, typically in a grid in the plane. All right, digital topology. Anyway, first I want to talk about 4 theorems about the Euler characteristic. These are some actually kind of obscure theorems, although I think they should be better known. So maybe it begins right here, the rehabilitation of some of these theorems. They're not all obscure. Actually, one of them is quite well known. But anyway, we're going to talk, probably most of you know basically what the Euler characteristic is, but just in case, our setting is going to be simplicial complexes, or polyhedra, if you want to say it another way. That is things that look like this. So there's spaces which are made up of finitely many points, which I may refer to as vertices, and then they have some edges between them. And then also, sometimes there are some faces, like these flat sort of planar type things. And then you can also have like tetrahedron kind of things which have a volume inside them. All right, anything like that or higher dimensional versions of that sort of thing, those are called simplicial complexes or polyhedra. So this is called a complex, and then each of the things, like each vertex by itself is a simplex. Also, each edge is a simplex of dimension 1. A vertex is a simplex of dimension 0. You have faces, which are simplices of dimension 2, etc. All right? And the Euler characteristic. So if you have any complex like that, then I'm going to say Vi of x is the number of I-dimensional simplices. So V0 is the number of vertices. V1 is the number of edges. V2 is the number of those two-dimensional faces, etc. So for example, for this one here, those numbers, the V0 is 18. You could count those up, see if I did it right. There are 23 edges here, 8 faces. You can see there's 4 here, and then this tetrahedron thing has 4 faces, so there's 8 total. And then one solid thing, the inside of the tetrahedron is a 3-dimensional simplex. And then there are no higher dimensional ones. All right, all the other VI's are 0 in that example. And the definition of the Euler characteristic, you add them up, but you alternate the signs like that. All right? And I put this dot, 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 but really this is not actually going to be an infinite sum because it ends after a certain point, because I said there are always going to be finitely many vertices, so you can't have infinitely many simplices. Anyway, in our example, if you do that, you get 2 when you add them up like that. All right, that's the Euler characteristic. Pretty awesome, right? Maybe. Okay, the Euler characteristic has lots of nice properties. And if you know anything about the Euler characteristic, you probably know this property here. It is called a subdivision invariant. It means if you have a complex or any kind of a shape and you put some sort of a subdivision of it, you divide it up into triangles and edges and faces and all that stuff. Actually, if you divide it up in 2 different ways, you're going to get the same number when you do that alternating sum of the number of vertices and edges and whatever. So you could, in theory, this would be kind of a pain to do on the right, not so hard on the left. But anyway, if you did it either way, you get the same answer. And in fact, in this case, the answer is 1, just because I know something about Euler characteristics. The answer is 1. All right. It's also a homeomorphism invariant. That means you can not only can you re-subdivide the shape, but you can actually change the shape in certain ways. And if you know any topology, the ways which I'm referring to are homeomorphisms. Vaguely speaking, you can sort of stretch and compress the shape around. You can change its shape, but you can't rip a hole in it or glue 2 pieces, sort of removing a hole from it. All right. But these 2 things are homeomorphic because you can get from here to here by just kind of crunching it up a little bit without ripping or gluing. All right. And it turns out the Euler characteristic is a homeomorphism invariant. And these 2 also have Euler characteristic 1. In fact, because the square is homeomorphic to the triangle, all these things have Euler characteristic 1. All right. It's also what we call a homotopy type invariant. These two spaces, so this sort of, I don't know, Chinese coin shape. They're Chinese coins look like that. And then that empty circle there, they're not homeomorphic, but they are homotopy equivalent is the word for that. You should think of that as you're allowed to do this sort of compressing. Again, no, you're not allowed to rip any new holes in it, but you can kind of compress things all the way down to lower dimensions sometimes, and that's called the homotopy equivalence. All right, those two things are homotopy equivalent to each other, and the Euler characteristic is the same for any two spaces which are homotopy equivalent. All right, in this case it's 0, because the Euler characteristic of a circle is 0. Isn't that convenient? Because right, that's cute. Okay, another nice property, it adds up nicely on disjoint sets. If you have a space which consists of two like disconnected things, then actually the Euler characteristic of that whole thing is equal to the sum of the two Euler characteristics. That should seem fairly clear if you think about just the definition of the Euler characteristic is you make a subdivision and then you add a bunch of stuff up, right? So if you have A and B and they're totally separate from each other, they're not interacting at all, when you add up all the stuff in the whole space, A union B, that should be the same as adding up all the stuff from A and also adding up all the stuff from B and adding the answers together, because there's no interaction between them. There's no overlap or anything like that. All right? This is kind of like a disjoint unions property for the Euler characteristic. Actually, it's even better than that. If A and B are not disjoint, then you get this property. So this, if A and B have some kind of overlap, you can still do sort of like that disjoint union thing, only you subtract out the intersection. All right? And it's also true that the Euler characteristic of the empty set is 0. So this is a more general statement than the disjoint union one. In the disjoint union case, the intersection was empty, right? And then you get exactly what it said before. But this is a stronger version of that. Actually, there's a name for this kind of a function. It's, let me say, this property here is also referred to as the inclusion and exclusion property in combinatorics. You may have heard of that. If you want to say, if A and B are just sets of things and you want to know how many things total is in the set A union B, it's equal to the number of things in A plus the number of things in B minus the number of things that are in both, because you would have double counted if you add. So this is a very common kind of a formula that you see in combinatorics. It's called the inclusion and exclusion. Anyway, things like this are called valuation. So the Euler characteristic is a valuation. It means it satisfies this inclusion-exclusion property. All right. Okay, two more properties that are a little slightly stranger. There's a quotient property for topological quotients. I don't really intend to get into this so much, but if you know some topology, you probably have seen this. X modulo A means you take the whole space X and you collapse this A, which is a subspace of X. You collapse A down to a point, and then you sort of bend around the rest of the space to accommodate your collapsing. And it turns out this is what you get. The Euler characteristic of the whole space is kind of additive with respect to quotients, although you've got to add this extra +1, which is, you could say, is kind of because when you collapse A to a point, everything which was A becomes a new vertex, and you have to account for the fact there's a new vertex. But this is a nice quotient property for the Euler characteristic. And then there's also this. This is probably the weirdest one. This is a local formula for the Euler characteristic. I don't care so much about what's in the parentheses here, but the important thing I want to mention is this. You can compute the Euler characteristic on the whole space by just adding up a bunch of stuff where the stuff you're adding depends only on the region around each vertex. So the star of a vertex, technically this is the open star. It's the star of a vertex is defined to be all the simplices which touch that vertex. It's something like a local neighborhood of a vertex in a simplicial complex. All right. This is a formula. In fact, you can compute the Euler characteristic of the whole space by adding up a bunch of stuff that only depends on the stars of each vertex. It's a little weird. Actually, it's quite weird when you see this here, this fraction, because in this formula you're adding up a bunch of things which are not integers because they have this fraction in them. But it turns out by some kind of magic, they're going to add up to the Euler characteristic, which is always an integer. All right, it's kind of nice. Yeah.
In the first formula, it doesn't look like it comes out right if A is a point.
Then, maybe a -1.
Yeah.
Yeah. Yeah,
Or
actually,
be the reduced one, I care.
yeah, the way this formula is typically not written this way, and I was translating and I think I messed up the... Does it work if it's a -1? Then these are the same. This is 1. Yeah, and if you subtract 1, you get 1. Okay, thank you for that. That's a minus. I think I've repeated this mistake later on, but it doesn't really matter. All right, thanks. Yeah. Anyway, this local formula works for the Euler characteristic. Okay. Here's my 4 obscure theorems. You know, the Euler characteristic is, I believe this is true. I'm not an expert in the history here, but I think the Euler characteristic is the original sort of numerical topological invariant. I have a friend who wrote a book about the Euler characteristic, and I asked him, are there any earlier ones? And he said, I don't think so. So that's proof enough for me. But you might say it has kind of a weird definition. I found myself, I don't recommend this, but I found myself explaining to one of my friends who's not really into math what the Euler characteristic is. And I said, oh, you take a shape, you draw a bunch of triangles on it, and then you add things up and subtract things in this way. And her immediate response was, well, why do you do it that way? And I said, well, because that, if you do it that way, then it has some nice properties. And I guess if you did it some other way, it probably wouldn't have any nice properties. Or if you just made up your own thing, it probably wouldn't mean anything. You might say the definition is a little weird. When you see it for the first time, at least, it should probably cause you to wonder, why exactly should you do it that way? For instance, in particular, why do it with the alternating sign? Is there something else where you just add them all, like with pluses every time? Why isn't that a thing? Like the Stecker characteristic. It's not a thing because it's not good for anything, really. But these questions should occur to you when you see a definition. It turns out that this particular way of adding them together, adding and subtracting with plus and minus 1, is actually one of the only interesting numerical things which makes much sense at all. There would say if you put plus signs everywhere, that thing that you would be talking about wouldn't be good for anything. All right. And that's what the 4 theorems are trying to get at. Each of the theorems is a uniqueness theorem for the Euler characteristic. It says something like the Euler characteristic is the only function which has this or that nice property. All right. Actually, I hope you don't mind me getting a little heartfelt here. I really love uniqueness theorems. This is like ever since I started, like since I was in college, I really got into uniqueness theorems. Because, I find myself, especially when I'm learning some new math, something which is new to me, which seems really complicated, I always find myself thinking like, man, do I really have to do this crazy stuff? Like, isn't there some better way to do this or something like that? It seems to me uniqueness theorems kind of clear that up in my mind. They sort of tell us that the concept you're talking about is really one that's sort of from the book. I don't know if you've heard of the book. This is a sort of mythological, mathematical legend that a mathematician named Paul Erdős used to talk about the book. And he sort of imagined that there is somewhere in heaven or somewhere deep inside all of our hearts, there's the book which contains all of the perfect proofs of all of the mathematical truths in the universe. And Erdős was known to say things like, if he saw a proof of a theorem but he didn't like the proof, he would say something like, okay, your proof is correct, but I want to know the book proof, meaning the sort of most beautiful and most true statement of what you were talking about. And when you're talking about if you encounter a new mathematical idea, at least I do, I find myself wondering, is this really in the book, or is this just something I made up and is just stupid because I don't understand things well enough? Like, am I really onto something here, or is this just sort of my own abstract nonsense, which doesn't mean anything? I always feel like if I have some kind of a uniqueness theorem, that demonstrates sort of that this concept exists and it's the only way that it could possibly exist. So I must be onto something. That's sort of how I feel. I don't know if you ever felt this way. This is a quote from Erdős. You don't have to believe in God, but you should believe in the book. Whether the book is a real thing or just something in our imagination, I think it is nonetheless sort of a working assumption, or at least an attitude that most mathematicians have. Even if, sort of technically speaking, you may not believe that mathematical truths like have some sort of independent existence. You still kind of operate in that way when you're investigating something. You're trying to explore something, a new idea. Everybody kind of has at least some sort of deep down feeling that what they're studying is something actually real, and that we are looking for truths which are either true or false, and we're just trying to figure out what they are. Anyway, believing in the book, something that's helpful sometimes. Oh, okay, here's the theorems. You're probably anxious by now to see the 4 different uniqueness theorems. Here they are. These are the titles. This is so. This right here is actually a book. The other 3 are in papers, but and I don't actually know what that means. Anyone? Experts? Contents. Okay, so that would be like volume. I know. Maybe.
Last one was like isoprene or something.
Like lectures or something like that.
Okay, lectures on volumes, perimeters, maybe, and Oberflakes. Whatever that is. I don't know. I know what the theorem is, but I don't. Okay, here's. I put them in chronological order here. Watts on the Euler characteristic of polyhedra, which is a little vague. This is Wall. This is CTC Wall. It's actually a very famous geometric topologist. Another somewhat vague title. And then the latest one is Levitt, the Euler characteristic. This has got a very specific title. Euler characteristic, unique, locally determined numerical homogeneity. Right. There may be more, actually. These are all of the uniqueness theorems for the Euler characteristic that I'm aware of, although maybe I'm missing some. Although even these are fairly obscure. So Hadwiger's theorem is actually very famous, at least among certain people. But other than Hadwiger, these other 3 are very rarely cited. I did a little research on this one. Here's a graph of their citations of each other. So they, for the most part, they don't really seem to be aware of the other uniqueness theorems. Although, I mean, Hadwiger was first, so he's not going to cite the other ones. But Watts and Wall did not reference Hadwiger, and Levitt only referenced Wall. That's a complete graph. Here's a little total number of citations of these works to give you an idea of how obscure some of these are. Hadwiger's book has 154 citations. Like I said, Hadwiger's book kind of gave birth to a whole discipline in topology, so it's a big deal. Watts's paper, 3 references. This is a list in decreasing order of references, so it's not going to get any better than that. Levitt has 2, although he's the most recent, but mid-80s is not terribly recent. And Wall has 1. This is
From Levitt, right? Yeah.
yeah, right. Yeah, from Levitt, right.
Specific category.
Levitt cites Wall.
One of Levitt's is Wall.
No, Levitt references Wall. So this says,
the list of
Ever
people who
referenced
cited
Wall?
yeah, Wall's paper has never been referenced by anyone but Levitt. Right.
Add one now, which is not great.
Yeah, right. So I got this from, there's a database that's maintained by the AMS called MathSciNet, and these are the numbers from MathSciNet, which it only encapsulates certain types of publications and certain ones. So there's probably a little bit more than that. And actually, I happen to know Watts's paper, MathSciNet will tell you it only has 2 citations, but I actually, because I know something about these papers, I've actually seen another one, so I jack it up to 3. So there may actually be more of these.
It's a book. They don't do a bibliography of a book or any long volume. It's only
Okay. All right. Yeah. So they're probably artificially low. It's a little surprising that I would say of these 4 guys here, Wall is easily the most sort of well-known of them all. But this must be like Wall's worst paper ever. He was very influential. Anyway, so let's just go through them each just briefly. I'm not going to get into any of the proofs. Hadwiger's theorem is the most famous, and Hadwiger focuses on the valuation property. Here's the theorem. I say 1950, so the title I put up there was his book. He sort of wrote 5 or 6 papers which had the general results, and then he sort of compiled them into a book, so it's hard to say exactly when. Anyway, if epsilon is any kind of real number valued homeomorphism invariant. So you should imagine something like the Euler characteristic, which you compute this on a space and you get a number, right? It doesn't have to be an integer, though. Anyway, any invariant which obeys this valuation property and also has this property that epsilon of a single simplex equals 1. Anything like that must be the Euler characteristic. That's the theorem. So I said, the Euler characteristic is a valuation, and it also has a property that the characteristic of a simplex is 1. The Euler characteristic is the only function like that. So this is Hadwiger's theorem. Actually, Hadwiger's theorem is quite a bit more general, which is why he wrote a whole book about it. Hadwiger actually, his theorem is about any functions which satisfy just the first property, not necessarily the second one. There are lots more functions which satisfy just the first property. For instance, the volume of a space. If you have a geometric space, its volume satisfies that inclusion and exclusion. Also things like the perimeter or the surface area, these things. Anyway, Hadwiger's theorem, the big theorem, classifies all possible valuations on subsets of Rn. It's very powerful. And I don't think any of you students were there, but I gave a talk about Hadwiger's big theorem at the REU last year, which none of you were part of. Although, if you want, check out, I put it on YouTube if you're interested, Hadwiger's theorem. I called it all kinds of big. Check it out, yeah. More general, that's what I just said. Okay, let's talk about Watts. Watts's theorem focuses on the quotient property. I'll level with you right now. When I gave you all those properties of the Euler characteristic of being, I wasn't just choosing them at random. They actually were the properties which were used for the uniqueness proofs. The quotient property, which again should be a -1 here instead of a +1. Anyway, this is Watts's theorem. If epsilon is any integer-valued homeomorphism invariant, which has the quotient property, and also satisfies this, that whatever this thing is, when you do it on two separate points, you get 2, all right? Then it must be the Euler characteristic. So the Euler characteristic is basically the only thing which has this quotient property with the -1.
Chris?
Yes?
So the previous theorem had real value, this one is integer value.
That's right. Yeah, and this is something I'm going to mention in a little bit. So Hadwiger's theorem says, even if you assume your invariant is not integer valued, actually it has to be integer valued because it has to be the Euler characteristic. This one says, if you assume up front that it's integer valued, then it has to be the Euler characteristic. You should wonder, does that mean perhaps there are some real valued functions which satisfy these that are not the Euler characteristic? The answer to that is also no, but Watts didn't say that in his paper. But yeah, I'm going to mention that in a bit. Watts's proof is actually very nice, but don't read the paper. It took me a while of reading Watts's paper and thinking it was way too hard for me to understand. And then I realized that actually it's not very hard at all to understand, but it's written in a very strange way. So talk to the folks in my group about the proof. We worked through the whole proof, I think, on our second day of the summer. It's very nice. It's a nice argument, presented in my opinion, a very strange way. Anyway, this result I ought to mention. This was generalized to another invariant called the Lefschetz number by Arkowitz and Brown. This is Robert Brown, who is my dissertation advisor at UCLA, and I've actually done some work that's similar to this kind of generalization. This is how I found out about the Watts paper, was because Bob was working with it. Okay, let's talk about Wall's theorem. Wall's theorem is about any kind of simplex counting invariant. So this is Wall's theorem. If you have an integer-valued subdivision invariant, which is a linear combination of those VIs, right? Remember, the Euler characteristic is those VIs with plus signs and minus signs in between. But you could imagine, what if I added them together in some other way, say using all plus signs? Or maybe put some number coefficients in front of each one? This says, don't go there. So Wall's theorem is the only possible linear combination of the VIs, which is a subdivision invariant, is the Euler characteristic, or possibly some constant times the Euler characteristic. So if you put, say, instead of plus 1s and minus 1s, you put plus 2s and minus 2s. That is just 2 times the Euler characteristic. That's still a subdivision invariant. But those are the only possible sort of, I could call them simplex counting invariants. If your invariant is somehow based on counting up the number of simplices of various dimensions, the only way to do it is the Euler characteristic, which is pretty cool, I think. Yeah, the only linear combination of the VIs, which is subdivision invariant, is specifically the one with plus minus ones or a constant multiple of that. That's Wall's theorem. And then the last one, Levitt. So Levitt focuses on this local formula thing, this somewhat strange way that you can compute the Euler characteristic on the whole space by adding up sort of little Euler characteristics in each neighborhood around each vertex. All right. Here's Levitt's theorem. Again, you can see the values changing sets. But if you have a real valued subdivision invariant, which can be computed in terms of any local function, so anything which involves adding up some values in the region of each vertex. D can be any function at all. As long as the whole result is a subdivision invariant, then, again, it must be the Euler characteristic, basically, or a constant times the Euler characteristic. All right? So there is no other kind of a thing that you can compute by adding something up at each vertex, which is a subdivision invariant. All right? That's Levitt's theorem. That's pretty cool, too, I think. Okay, here I'm going to talk a little bit about the group of values that you get. So the Euler characteristic is the only integer valued invariant that satisfies all these properties. But you should wonder about what about real valued invariants? Maybe there's some real valued invariant which satisfies the properties which is not the Euler characteristic, or perhaps complex valued invariants, or maybe Z adjoin X, that would be a polynomial valued invariant. I'm sure you've all heard of, like, or you math folks at least, there's something called knot theory, and knots have polynomial invariants associated to them. So you might wonder, like, is there such a thing as, some kind of a Jones polynomial of the general topological spaces? Can you generally satisfy? This would be some reason, at least, to look for things which are not just integer valued invariants. Anyway, you can trivially modify most of these theorems to show that, in fact, it doesn't matter what set you assume the invariant to lie in, whether it's Z or R or whatever. Most of the theorems show that the Euler characteristic is a unique invariant whose values live in any abelian group. So, for instance, say in Wall's theorem, which had a Z rather than an R, in fact, if you let G be any abelian group and assume that your invariant satisfies that quotient property and it has its values in G, then the values of your invariant must actually equal some chosen generator of G, which you imagine to be like 1 times the Euler characteristic. These things typically can be made much more general than the statements that you'll see in the paper. All right? Okay, that's the end of those 4 theorems. Anyway, let's get back to the digital topology, which is what kind of our summer project is really about. So here's that digital space invader again. And I want to consider this as a finite set of pixels in Z2, that is the integer lattice, rather than as a subset of R2. You think of it as a finitely many pixels, and they are next to each other in that way, right? If you know something about topology, you might consider the natural thing to do typically is use a subspace topology from R2. I should have said R2, not R3. Well, I guess it doesn't matter, but I meant R2. Can anyone tell me why that's a bad idea? Or it turns out that actually doesn't really get you anywhere. If you take this finite set and then use the subspace topology from R2. One of you in my group can say if you want.
You just get a bunch of points, so it's not very interesting.
Yeah, you get the discrete topology if you do that. If any finite set in Rn, if you use the subspace topology on it, you get a discrete topology, which means there's not much you can say about it, or there's not much you can't say about it. Anyway, you don't want to use the discrete topology to say anything nice about the space invader. All right, it requires sort of a special theory. The whole discipline of digital topology is fairly new. I mean, to be generous, you could say since the 60s maybe, people have been trying to do this sort of a thing. You could say, I'm not an expert in history, again, and I'm not an expert in the foundations of math, but from where I'm standing, at least, it seems like the development kind of mirrors the early history of formal mathematics. So the very early work in digital topology was done like in the 60s and 70s with little concern for theory building. This is like people saying, I want to write a computer program to tell the difference between the letter A and the letter B. And don't bother me with your Euler characteristics or whatever. I just want it to work. A lot of the original work was done in that style. And that, I believe, is kind of, this is sort of like mathematics in the ancient times. People use math just to do stuff. And people were doing stuff like what we do in digital topology for quite some time before anybody tried to really sit down and give it a real sort of theory to it. They were just trying to get the job done at that time. But by the time you got to the 90s, there were actually several different models for doing digital topology. They are clearly related, but they're not really equivalent. And when you look at papers in digital topology, they usually say, sort of at the beginning, here's the kind of digital topology I'm going to do in this paper. And they're really sort of different ways of doing it. I'm not an expert in this, but just informally, I can see at least 3 different sort of major schools of thought on what digital topology, how you should do digital topology. There isn't really a single standard model yet, and I'm not sure there's a good reason to think that there ever will be. I mean, this is a very similar situation happened in mathematics at large at the beginning of the 20th century, and we eventually more or less settled down on sort of the ZFC model of set theory. There were alternative models, and there still are alternative models, but basically everybody uses that model. And nobody, typical mathematicians don't really think about all that stuff very much. I don't know if a similar thing is going to happen in digital topology. Probably not, but I guess we'll see. Anyway, we're going to take what I'm going to refer to as the graph theoretic approach to digital topology, and I'm not really going to mention much about the other ones, although I'd be happy to explain a little bit to anyone who wants to know, or people in my group could also. So the graph theoretic approach starts with the basic idea that all the topological information in a set of pixels is determined by their adjacencies. It's a bunch of pixels, and they are next to each other in certain ways. All right, and that's really the only important thing about them is which ones are next to which other ones. All right, so in that sort of idea, you say a digital topological space is a set. I should say a finite set. Typically, they're finite, although you could do this. You could do some things for infinite sets. Typically, you assume that it's part of the integer lattice in the plane, or maybe an integer lattice in the 3 space, which has some kind of symmetric adjacency relation. That is, there is some idea of certain pairs of points are either next to each other or they're not. All right. That's what a digital topological space is. All right. Unlike ordinary topological spaces, you don't really talk about open sets in this model of digital topology. There's just points, and certain points are next to certain other points, and that's it. But you can still define a lot of the classical topological notions, even without using infinite sets. I mean, even without using open sets. For instance, paths, loops, connected components. So connectedness is defined in terms of path connectedness. You can define continuous maps as the image of a connected set is connected. That's the definition that's typically used of continuous maps, which is not exactly equivalent in classical topology to the preimage of an open set being open, but if you're considering only finitely many points, it sort of is equivalent. You can even define homotopies between maps, homology groups, homotopy groups like the fundamental group, etc., if you know what those things are. All of these things have been worked out in this graph theoretic approach to digital topology. There's cohomology theories also. All that great stuff. All right. In Z2, so if you're thinking about a digital image just like in the plane, these spaces are sometimes called digital images also for obvious reasons. There are 2 typical adjacency relations that you'll see depending on whether or not, if you just look at that space invader and I ask you, which of these points are next to which other points? Sooner or later, probably sooner, you're going to ask, well, does diagonal count as next to? And I'll say, maybe. So these are the 2 different ways of measuring adjacency that are typically used. Depends on whether diagonals count. So I hope you can see the red lines there. This is referred to as 4 adjacency because every point is adjacent to 4 other ones, at most 4 other ones. All right. This is sort of the no diagonals allowed version or relation for adjacency. And then there's also, this one is called 8 adjacency, where the diagonals are allowed. All right. And the space has different topological properties depending on whether you're considering with 4 adjacency or with 8 adjacency. So topological properties of space are different. For instance, with 8 adjacency, this is a connected space. That is to say, you can get from any pixel to any other one by following a sort of a trail of adjacencies. But with 4 adjacency, it is not connected. Can anyone see where this thing fails to be connected? You can see it's in the the ears and also these mandibles or whatever those are. They are not connected onto the mainland of the rest of the body, right? If you're using 4 adjacency. And you just have to, if you're actually using this in applications, you just have to decide ahead of time which way you're going to do it, depending on what you're doing, what kinds of properties you're trying to measure. One or the other may be more useful to you. Or you could use any other type of adjacency relation. There's nothing really special about the 4 adjacency versus the 8, and there are other things you could imagine doing. So this is sort of a slanted adjacency. I'm allowing only diagonals which go in the sort of up and right direction, but I'm not allowing the other diagonals. All right? This is allowed. You might wonder why we would want to do this, but it's a legal digital topological space, right? Or this one here goes the other way. Did you see the difference? Right? So this one goes the other way. They are different spaces. Actually, I think in this case they would be homeomorphic because you can just reflect the whole thing and you'll get the other one. But, at least perhaps they are different spaces. All right? Here's one. This is one in which every pixel is just declared to be adjacent to every other one. Not terribly useful, but this is a legal digital topological space, right? Digital space consists of a bunch of points and then some assignment of adjacencies. Doesn't have to be nice looking, right? Here's another one. Can you see the lines? Yeah, there are no adjacencies in this one. This is like the discrete digital topological space, right? No connections anywhere. Or here's another one. I just chose adjacencies at random. I'm just trying to prove to you. It doesn't have to be any kind of nice formula or whatever that decides the adjacencies. You just need some notion of adjacencies. All right. Anyway, we can define a simplicial structure on these. Like you can actually realize these digital spaces as simplicial complexes in what is mostly an obvious way. So each point you consider to be a vertex by itself. What should you consider to be edges in your space? I think it's natural to consider just each of those little red lines. Each individual adjacency defines an edge, okay? Now it gets a little weird, but not too weird. Each set of 3 mutually adjacent vertices makes a face, a two-dimensional simplex, right? So that would be, sort of triangular-like things like that, right? That's a face, all right? Each set of 4 mutually adjacent vertices makes a 3-simplex because the 3-simplex in classical topology at least is a tetrahedron, which is defined by 4 mutually adjacent vertices. So this is a sensible way to do it. And then, etc., right? If you have more than 4 mutually adjacent vertices, that would be a higher dimensional thing. All right? Given that definition, you can do this. You can just add up the number of simplices in each dimension, alternating the sign, and you get something which is called the Euler characteristic of your digital space. So let's just try it on this one. With the 4 adjacency here, you can see, so actually each little red circle is a vertex. Each one of those lines there is an edge. And in this case, there are no faces because with the 4 adjacency, actually, it's impossible to have 3 mutually adjacent vertices. You would have to have a picture like this, but there's no way of doing that with this adjacency relation. So you can say, and you could go count them if you wanted to, there are 46 vertices there and 55 edges. And no higher dimensional ones, and so the Euler characteristic is -9. How do you like that? All right. Okay, how about with 8 adjacency? It looks like this. Now on this one, actually, you are going to get quite a lot of these, actually. And this time we will have 2 simplices. And in fact, you will have 3 simplices here because there are certain sets of 4 mutually adjacent vertices. And I kind of colored them in here. So you can see the green guys are the 2-dimensional simplices, and the blue guys are the 3-dimensional ones. And each of these blue guys actually has 4 green guys as its four faces, but I wasn't sure how to color that in. So that's that. Anyway, now you can count them up. Each green thing is a 2 simplex. The blue things are 3 simplices. This time, if you count them up, that's what you get. Add them up, you get -1. All right. That's actually kind of a good news. That if you take this Space Invader and just look at it, like sort of fill in all the pixels and look at it in R2, it has Euler characteristic -1. So that's nice. Here's another one. This is the old mushroom. You can make simplices like this. Anyone see the mistake in this one? For some reason, I use a computer program to draw these pictures, and it must have a bug. Yeah, this right here shouldn't be there. I'm not sure why that happened. I figured it would be more interesting to just point out the mistake than for me to try and fix my code to... Anyway, if you do it this way, the Euler characteristic is 125 minus 283 plus 184 minus 31, which is -5. Great. Okay, let's talk about our project for the summer, which this whole talk is allegedly leading up to. So my idea for the project was I want to generalize some or all of these 4 uniqueness theorems to the setting of digital topological spaces, right? The Euler characteristic is the unique invariant in classical topology which satisfies these properties. So we should either be able, we should be able to do something like that in digital spaces. And I figured I got 4 of these theorems, right? So even if the first one doesn't really work out, we got 3 more to go for. So early realizations. No. Actually, there are like very. We realized certainly by the end of the second week, that probably none of these theorems were going anywhere. Here's why. Turns out Hadwiger's and Watts's formulas aren't even true at all for digital spaces. It turns out they just don't add up nicely in this way, even if you do use a -1 here. They just don't work in the graph theoretic model of digital topology. Actually, Hadwiger's theorem is something that does work in some of the other digital topology models, but not in this model. All right. And in fact, we tried. Nothing like these formulas seems to be true either. In fact, my group showed that even if you were to change the signs around here or insert some coefficients in here, no formula like this can be true for digital topological spaces. Basically, these 4 quantities here are linearly independent. That's what we showed. And similarly over here, these 3 quantities plus any constant is also linearly independent. So these formulas really cannot hold in the setting of digital topological spaces. So I'm not sure really that you can say anything like Hadwiger's or Watts's theorems in that case. Okay, what about the other ones? Wall and Levitt are about subdivision invariance. In a digital space, there isn't really any such thing as subdividing the space because that classically involves inserting a point in the middle of an old simplex, but you can't just jam an extra point into your digital space without screwing it up because it's not smooth in between the points. There is no real in between of the points. All right. There's no subdivision invariance, so I figured we'll just use homotopy type invariance instead, invariant under homotopy equivalences, which the Euler characteristic is. But it turns out, as we discovered, the Euler characteristic in digital spaces is not even invariant under homotopy equivalences. So a lot of things that I thought were going to be kind of, in my mind, I said, all right, first, as a very basic thing, we'll have to show that the Euler characteristic respects homotopy equivalences. And then we'll get on to the better stuff. But it wasn't true even at the beginning. So this is actually fairly, at least in my experience, this is kind of what math research is like, though. You have some ideas, and some of them are good ones, and some of them are bad ones. So there's a lot of questions that remain then. If the Euler characteristic is not invariant under homotopy equivalences, what is it invariant under? I feel like it should be invariant with respect to something, but it's not homotopy equivalence. It obviously is invariant under homeomorphisms, but what else? That's a question that we have. Another question is, if the Euler characteristic is not invariant under homotopy equivalence, what is? Are there any numerical homotopy type invariants? And this is something that we've been looking at. The answer is yes, we have a few examples of them. So what are they? And can you get some kind of characterizations of these, like a uniqueness theorem for one of these other invariants? All right. These are things that we are vaguely thinking about. Although more specifically, we've been thinking about this lately. How can you decide which two spaces are homotopy equivalent, have the same homotopy type? This is something that's very well understood in classical topology. And if you basically, classically speaking, if you draw me any two shapes, I can more or less immediately tell you if they're homotopy equivalent or not. That is not at all true in digital spaces. And so this is what we've been thinking a lot about lately. I could say a lot more about what we've been doing, but I think I'm going to leave that to my folks for next week. All right, that's all. I'll just let you know. All the pictures of the Space Invaders and whatever were generated with a really cool programming language called Processing. It's a sort of a Java-like language, which is specifically made for generating pictures of things. So check it out if you're into that. That's all. Thanks.